Hi there, Paul again. So, in the last part, we learned about the perceptrons, and we found out that perceptrons are great if you have a linearly separable problem, but if the problem isn't linearly separable, then you can't. The perceptrons can't work. So, it works out that if you have networks with more than one layer, so not just the output layer, but also hidden layers, maybe, then they can learn problems that aren't linearly separable. The problem was no one knew how to set the weight values for a particular training set. So that was until the backpropagation algorithm was discovered or developed. And that was 1974 by Paul Werbos, but popularized by Rumelhart and others in 1986. And we're going to go through backpropagation a little bit later, but first off, let's just look at multi-layer perceptrons or MLPs. We've already seen one, so this is what we saw before. We have an input layer, which isn't trainable. We have a hidden layer, which is trainable, and then we have an output layer, which is trainable. And the weights are the weights we're going to set. If it was so the perceptron would just be like inputs going straight to the output. As I said, we're going to have our bias nodes, which we saw before, and they also have weights. And we use the same trick that we used with the linear discriminants, where we augment the vectors to be able to deal with the bias nodes. Just to remind you, the output of each neuron, so in this case neuron J, is a function of the dot product of the weights and the input values. And often we use the sigmoid function for that activation function. To remind you, the activation function the sigmoid function looks a little bit like that. So with the multi-layer perceptrons we'll be looking at in this class, we're interested in networks where the connections never go back to a previous layer. So they always go from the inputs to the hidden to maybe a second hidden and then to an output. That's called a feed. They're called feed-forward networks. If the connections go back, or if you have a connection to the neuron itself, the same neuron, that's called a recurrent neural network. And those little loopy connections back to themselves, they act as little memories, and they can handle situations where you have a sequence of data. The problem is it's much more difficult to train that kind of a neural network. So we're not going to be looking at those in class. So with our feed-forward networks, if we want to find the output of the network, we feed the inputs into the input layer, and then we calculate the outputs of the first hidden layer, then the second hidden layer, and all the way through to the output layer. So the values feed forward through the net. So it turns out that multi-layer perceptrons can model any continuous function in a 3-layer sigmoid neural network. Sybenko showed that in 1989. Problem is you may need many neurons in the hidden layer. Also, the theorem says that it's possible. It doesn't say how to find the proper network structure. And then Hornick in 1991 showed a similar kind of thing. He showed that the type of activation function, whether it's a sigmoid or not, is not so important. It's this multi-layer feed-forward architecture which is the real way that you get the expressive power of these multi-layer perceptrons. So there's two big challenges that we're going to find with using the multi-layer perceptrons. First off, we need to decide on this network topology. How many hidden layers and how many neurons in each of the hidden layers. And then the second thing we need to work out is how do we set the values for these weights, which make the network produce the correct output values. We're going to look at the second of these problems about finding the weight values first, but that's in the next part of the lecture.